Look at these two images. They're just random dots. But if you cross your eyes and let the two images merge, a shape suddenly appears, floating above the dots. Your brain uncovers the underlying 3D scene that explains both images. In this video, we'll use that idea to understand how AI learns useful world models, systems that predict what happens next, and why JEPA became such a promising architecture. Let's work with a simpler example. Here, the left and right images are simply offset versions of each other. One simple approach is to give both images to a neural network and ask it to predict depths. That setup is supervised learning. But this only works if we already have the correct depth label for every pair. So the real question is, can the network learn depths from the relationship between the two views without any labels? Here was Becker and Hinton's key idea. Take two networks, show each one a different view of the same scene like two nearby patches, and train their outputs to agree. If both views come from the same surface, the network should learn the things they have in common. So we add a loss that rewards agreement. But there is an immediate trap. The easiest way to make two outputs agree is to make both outputs constant, regardless of the inputs. This failure mode is called representation collapse. A collapse means the model produces nearly identical output across the board. The model has technically minimized the consistency loss, but learned nothing useful. Instead, we can measure the agreement between the outputs from the two views. For instance, imagine we have 6 numbers from the first network and 6 from the second. Now, how do we quantify the agreement between these two views? First, compute two things, the sum A plus B and the difference A minus B. If the two views share a real signal, the sum emphasizes what they have in common, and the difference emphasizes what changes. In this case, we believe that the two views share the same depth. The variance here indicates whether the outputs genuinely respond to different inputs. If it drops to 0, the model has collapsed. So we maximize the variance of the shared signal and minimize the variance of the disagreement. That pushes the networks toward the structure both views have in common. Under a Gaussian noise assumption, this is equivalent to maximizing mutual information between the two representations. Mutual information measures how much knowing one view tells us about the other. In other words, the two views become useful when they reveal the same hidden cause. Under these assumptions, maximizing shared information helps avoid the trivial constant solution. This approach is called IMAX, short for information maximization. IMAX enables a neural network with no built-in depth labels to discover depths from random dot stereograms. The limitation is that IMAX relies on strong assumptions, Gaussian variables, and symmetric agreement between the two networks. A simple way to make agreement harder to fake is prediction. Train an MLP to use part of the output to predict a held-out part. In effect, this acts as a regularizer against collapse. That worked, but only on tiny toy problems. To scale up, researchers moved beyond handcrafted agreement rules toward a broader objective: correctly match positive pairs and distinguish them from negative pairs. This is where contrastive learning comes in. To avoid collapse, we need the model to know not only what should match, but also what should not. Call one view the anchor, and another view of the same image the positive. Here, we use a neural network to extract each view into an embedding, a compressed description of what the model thinks matters. Our objective is to pull features from these similar images together. But if we only pull together similar views, the model can easily collapse. The key idea in contrastive learning is to introduce negative samples, that is, examples that should not match the anchor. Negatives give the model a reason to preserve differences, not just similarities. Now we can use this loss to push the negative away from the anchor. But if we only push negatives away, that force can grow without limit. The training may push the features from a negative sample arbitrarily far. A hinge loss fixes this by only caring about negatives that are too close. When their distance is sufficiently far, for example, larger than a margin m, the loss drops to 0. This push-apart term helps prevent collapse and encourages a more structured feature space. This solves the collapse, but the pairwise contrastive loss remains absolute. It pushes positives together and negatives apart based on fixed distance thresholds. A triplet loss makes the comparison relative. The anchor only needs to be closer to its positive than to its negative by a margin. Both loss functions help prevent representation collapse, but they still depend on choosing useful negatives. A single negative is a weak signal. If this negative is already obviously different, the model learns almost nothing from it. So we compare against many negatives at once. From here, we rename the anchor to the query and the positive to K+. We formulate a loss as a classification problem. Given a query Q, pick out its one true match K+ from a crowd of distractors. To do this, we score how similar the query is to each key, often with a dot product. We then apply a softmax function to normalize the raw similarity scores into a probability distribution. The goal is simple: give the positive key the highest probability. We minimize the negative log of this probability, which does two things at once. It pulls the query toward its positive and pushes it away from every negative. That matching game is InfoNCE, short for Information Noise Contrastive Estimation. A temperature parameter, tau, controls how sharp the probability becomes. Lower temperature makes the model more confident. Most probability goes to the top match. In contrast, when we increase the temperature, the distribution becomes more spread out. Now the bottleneck shifts. InfoNCE needs many high-quality negatives. InfoNCE starts with a similarity score, such as a dot product between the query and each key. The error signal from the InfoNCE loss can then be backpropagated all the way back to the query and key encoder weights. The simplest version trains everything end-to-end. But in this case, the dictionary of negatives is capped by the mini-batch size. This means we cannot afford to use a large dictionary of negative samples to compute an accurate loss. One fix is a memory bank. Pre-compute embeddings for every image in the dataset and reuse them as negatives. During training, we can sample negatives from this memory bank without backpropagation, rather than recomputing them at each step. This allows us to use a much larger dictionary of negatives. However, this solves one problem. It creates another. The encoder updates every step, but the stored embeddings of negative samples were computed by all versions of the encoder. Their representations become inconsistent over time. These stale negatives lead to unreliable updates. To alleviate the problem, the InSDisk method uses a momentum update on every sample to keep the negatives consistent. The downside is that this step is memory intensive and does not scale well. Instead of tracking representations for every sample, we use a key encoder whose weights are updated as an exponential moving average of the query encoder. So all negatives stay more consistent. This slowly evolving key encoder maintains a consistent dictionary of negative samples, resulting in more stable and reliable training updates. MoCo's core move is to keep many negatives consistent without tracking every sample. Now let's look at the queue that makes it practical. Let's work through an example. Here we have a dictionary of 16 negative samples. The exact number is just for the visual. The point is that the queue can hold more negatives than the mini batch. Due to GPU memory constraints, the mini batch size is capped at 4 samples. Given an input X, we apply data augmentation to obtain query and key images, then extract features from them. For example, here we have a new batch of query and key features. We use these anchor and positive samples together with the dictionary of negative samples to compute the InfoNCE loss. As training progresses, the dictionary is continuously updated by discarding the oldest mini batch of samples and replacing them with newly encoded features from the current batch. In other words, we maintain the dictionary as a first-in, first-out queue of data samples. This queue design breaks the dependency between the number of negatives and the mini batch size, enabling the use of a much larger dictionary of negative samples than what would be possible with a typical batch. Here is a comparison of 3 contrastive loss approaches on ImageNet linear classification. The momentum contrast method matches the performance of end-to-end training strategies, while enabling the use of a much larger dictionary of negative samples. This is MoCo, momentum contrast. So is this the best contrastive setup? It turns out there are 2 practical implementation details that matter a lot. First, for a given image sample, we should apply random combinations of strong data augmentations such as cropping, resizing, blurring, and color distortion. Augmentations quietly define what changes should be ignored. Second, we should add a learnable nonlinear transformation, such as an MLP projection head, between the representation and the contrastive loss. We can then apply the contrastive loss in this learn embedding space. Concretely, we compute pairwise similarity between all embeddings. Each entry in the matrix is the similarity between 2 embeddings. We highlight positive pairs with blue boxes and negative pairs with purple boxes. During training, the model learns to increase the similarity for positive pairs. Intuitively, we train the model to extract feature representations that are stable under different augmented views. That is the core idea behind SimCLR. This simple contrastive learning framework leads to impressive results. On ImageNet, these representations beat previous self-supervised methods when evaluated with a simple linear classifier. The cost is that SimCLR's end-to-end strategy requires very large batches. This plot shows that longer training and larger batch sizes are both critical. The second version of momentum contrast asks, can we keep MoCo's efficient queue while borrowing SimCLR's strongest training tricks? Here is the result of MoCo v1. SimCLR achieves higher performance, but this comes at the cost of requiring an extremely large batch size. The performance degrades considerably when we reduce the batch size to 256. The key implementation details of SimCLR are the learn nonlinear transformation and strong compositional data augmentation. MoCo v2 takes SimCLR's best ingredients and plugs them into MoCo's queue. It outperforms SimCLR and does not require large training batches, making self-supervised learning research more accessible. The same trend holds with longer training. At this point, contrastive learning has a powerful recipe. Positives, negatives, augmentations, projection heads, and a queue. Contrastive learning works beautifully, but it pays for that success with negatives. So the next question is, Can we learn without negatives at all? Given an input image, we create two augmented views, such as different crops. We call the two encoders the student and the teacher. Each has its own parameters. The student is the network being trained with gradient descent. The teacher provides the target that the student tries to match. We simply have the student predict the teacher's representation of a different view. So how do we prevent this from collapsing to a constant? We need two asymmetries. First, we update the teacher network as a slow-moving average of the student network, which makes its representations change more smoothly over time. Just as importantly, the teacher branch uses stop gradient, so it serves as a stable target for the student rather than being directly optimized to match it. Stop gradient means we do not update this branch from this loss. Second, only the student has an additional trainable nonlinear predictor head, while the teacher does not. This creates an asymmetry. The student must learn to predict the teacher's representation through an extra transformation, rather than trivially matching it. Together, the momentum updated teacher, the stop gradient operation, and the asymmetric predictor help prevent collapse. The goal is to prevent both branches from taking the same trivial shortcut simultaneously. This is BYOL. Bootstrap your own latent. Empirically, BYOL's representations do not collapse, even without negative samples or contrastive losses. The next question is, can we simplify this further? Let's first remove the additional prediction head from the student branch. Instead of matching a raw embedding vector in the representation space, we first apply a linear projection, then a softmax, converting the teacher's output into a probability distribution. The student is then trained to match this output distribution. We can interpret this distribution as a soft assignment over learned prototypes, without requiring categorical labels in advance. The model effectively invents its own soft categories, then training another view to agree with them. Similarly, we stop the gradient from flowing into the teacher network during training. To encourage the network to produce balanced, non-collapsed outputs, we apply centering. Centering subtracts the teacher's average output, which helps prevent one dimension or class from dominating. But centering alone can push the model toward a boring, uniform output. Temperature handles that balance. We set a low temperature for the teacher to produce sharp, confident outputs, and a higher temperature for the student for softer outputs. This balance of centering and temperature prevents collapse to trivial or uniform solutions, enabling richer, more meaningful embeddings. That recipe is DINO. Instead of using only two views, we create multiple crops from the input image. We make two large crops that cover larger regions of the image, called global crops. We also make several smaller crops that focus on local regions. The teacher model receives only the global views, which contain more comprehensive information about the image, whereas the student processes both global and local views as inputs. By using this strategy, the model learns to associate detailed information from small, local patches with the broader context provided by the global views. As a result, the model becomes better at recognizing objects and patterns, even when only small parts of the image are visible. The distillation family, methods like BYOL and DINO, avoid collapse through asymmetry. A slow teacher, stop gradient, and small design choices that keep the student from taking the trivial shortcut. These tricks are remarkably effective. However, relying on data augmentation has its own downsides. They depend on hand-designed augmentations. those augmentations may not transfer to every data type. And there is still no explicit anti-collapse loss. This pushes us toward a different source of supervision. Hide part of the input and make the model predict what is missing. Take an image, split it into patches, and hide most of them. We train an encoder that sees only the visible patches without masked tokens. We then use the encoded features from the visible patches, along with a lightweight decoder, to reconstruct the missing pixels using masked tokens and positional information. We call this a masked autoencoder, or MAE. Masking provides a flexible mechanism for creating different views of the data. Training a model to fill in the missing content presents a rich and challenging self-supervised learning task. To fill in what is missing, the encoder must learn both local patterns and the bigger structure of the image. This pushes the model to develop meaningful internal representations that go beyond superficial details, improving its ability to interpret and synthesize visual information. After training, we can discard the decoder and adapt the trained encoder for downstream applications. Here are the results on ImageNet image classification. We see something interesting when we compare it with a contrastive method like MoCo v3. When we freeze the trained encoder entirely, contrastive methods outperform the masked autoencoder. One likely reason is that contrastive methods use a discriminative classification style loss, whereas MAE relies on a reconstructive loss. However, when we allow additional blocks of the masked autoencoder to be fine-tuned using labeled data, performance rises quickly and soon surpasses that of MoCo v3. Because MAE reconstructs pixels, collapse is not the main danger. A constant representation cannot reconstruct different missing patches. Let's view the masked autoencoder from a different perspective. Given a masked input image, we use an encoder to extract a representation from the visible regions, and the decoder network conditioned on additional latent variables, Z, to reconstruct the original image. For instance, the latent variables Z tell the decoder which patch positions in the image are missing. Architectures like this are generative. They learn by reconstructing the signal itself. But when we force a model to predict every pixel, it ends up dedicating much of its capacity to recovering fine-grained details, textures, noise, color variations, or even compression artifacts that may not be relevant for downstream tasks. Joint-embedding methods take the opposite route. They compare views in the learned representation space rather than reconstructing pixels. Rather than low-level details, these methods produce abstract representations that capture shared semantics among related inputs. Examples include contrastive methods such as MoCo and SimCLR, and distillation methods such as BYOL and DINO. Joint-embedding architectures learn compact, abstract representations by matching different views in latent space, but often depend on carefully designed augmentations and risk missing fine structure. Generative architectures capture detail, but they can waste effort reconstructing irrelevant noise. So the goal is to keep the predictive challenge of generative models while moving the prediction into the representation space. Generative models predict pixels. Joint-embedding models match views. JEPA does something in between. JEPA predicts missing information in the embedding space by using context plus a small conditioning variable that specifies what to predict. This design focuses on meaningful structure without reconstructing pixels or relying on handcrafted augmentations. Let's see an example of this idea applied to images. We take the visible patches as an input, encode them, and predict the embedding of the masked target blocks in the embedding space. The variable z here specifies the spatial location of the masked target blocks. Here, z is basically the model's instruction: predict this part of the image. Different z values require different target locations. The answer depends on what the model sees and where it is asked to predict. Because the target location changes, the predictor cannot ignore where it is being asked to predict. It must learn to associate spatially conditioned features with each masked block, faithfully matching the encoding of the actual content at that position. This instantiation is called I-JEPA. In practice, I-JEPA learns strong semantic features while avoiding the cost of reconstructing every missing pixel. The same trend appears when fine-tuning with only 1% of the training data. The same architecture naturally extends to video. Images test whether the model understands what is missing in space. Video raises a deeper challenge. Can the model infer what is missing over time? We mask spatial temporal tubes and predict their features from the visible context. To do this well, the model has to learn that objects persist, motion continues, and actions have physical consequences, all from raw video. On the reported frozen backbone benchmarks, V-JEPA outperforms video pixel prediction methods. End-to-end fine-tuning yields similarly strong results, further validating the promise of latent space prediction. In V-JEPA 2, the authors explore an effective pre-training recipe for scaling up the model. Here, the y-axis shows the average accuracy. Starting with the original V-JEPA recipe, they scale up the video data, model size, training time, and spatial resolution. After pre-training, the point is that this strong frozen video encoder can be adapted to many downstream tasks using the same learned representation. For action recognition, we can add an attentive probe, a few transformer blocks on top of the frozen encoder. We can then recognize actions in the video and tackle prediction tasks that require a common sense understanding of the depicted situation. For visual question answering, we pass the extracted video features through an MLP. This turns the video into visual tokens that a language model can read. Now the language model can take a free-form question and generate an answer. For example, what changed on the table while the camera was looking away? To answer, the video encoder must learn to track scenes over time, remembering the past, inferring what's hidden, and connecting cause and effect across the video. Once the model understands how scenes evolve, we can pose an even deeper question. How would the scene change if the agent took a specific action? With the learned video representation, we can build an action condition world model. Action condition means the prediction depends not just on the current state, but also on the agent's chosen actions. We first encode the embedding from previous frames. We then train a predictor conditioned on robot actions and poses to predict the resulting future embedding. This gives us a powerful tool to predict how the world will change. A world model asks, if the agent is here and does this, what happens next? After post-training V-JEPA 2AC with less than 62 hours of unlabeled robot videos from the Droid dataset, it can support robotic planning tasks in the physical world. More specifically, starting from the embedding of the current frame, we roll out a chain of predictions through time. Conditioned on a candidate action sequence A1, A2, and so on. The rollout and score loop is called planning. We can search for actions that accomplish the task by checking how close the predicted final embedding is to the goal. Let's walk through a simple example to make this concrete. Imagine a 2D action space and 5 time steps. Assume this is the optimal sequence of actions for completing our task. How do we find this optimal action sequence? Here is a simple approach. We start by randomly sampling possible action sequences. Most of these random actions will not be very good. But for each candidate, we can roll the predictor forward and measure how close it gets to the goal. Then we keep only the best ones. The top-performing action sequences are known as the elite set. From the elite set, we feed a Gaussian distribution over actions at each time step. Now we can draw action candidates from these distributions. Repeat this loop, keep the best candidates, refeed the distributions, sample again. We obtain progressively better candidate action sequences. After just a few rounds, the top action sequences steadily improve, quickly zeroing in on candidates that achieve the goal. We call this optimization procedure the cross-entropy method, CEM. CEM is a guess and improve search. Sample many plans, keep the best ones, and sample again around them. This kind of planning is often called Model Predictive Control, or MPC. Traditional MPC often plans with hand-specified states and dynamics. Action condition V-JEPA 2 plans inside a learned latent state space, using a learned action condition dynamics model. So the same latent prediction idea now supports perception, question answering, and action planning. So far, many of the methods we have seen avoid collapse indirectly. BYOL, DINO, I-JEPA, and V-JEPA all use a slow-moving target encoder, often updated with an exponential moving average of the student's weights. EMA is a clever training trick. It gives the student a stable teacher to chase. But EMA does not directly constrain the representation itself. That motivates a different family of methods, redundancy reduction learning. Instead of pushing different samples apart, these methods prevent different dimensions of the same embedding from becoming redundant. Think of it this way. Every dimension should carry some useful signal, and different dimensions should not all say the same thing. The simplest version of this idea is whitening. Whitening is like rescaling and rotating the embedding so every direction is balanced. A covariance matrix tells us which embedding dimensions vary together. Given a centered batch of embeddings, whitening transforms them so their covariance matrix becomes the identity matrix. That means every direction has unit variance, and different directions are uncorrelated. A collapsed embedding has zero variance, so whitening directly rules out that trivial solution. The trade-off is that whitening can be expensive because it usually requires matrix inversion. Instead of explicitly whitening the entire embedding, Barlow twins constructs a loss that achieves the same effect. It keeps the redundancy reduction idea, but makes it easier to optimize. Barlow twins computes a cross-correlation matrix between embeddings from two augmented views. The diagonal entries are pushed toward 1, so matching dimensions agree across views. The off-diagonal entries are pushed toward 0, so different dimensions do not copy each other. In one sentence, Barlow twins aims to reconcile the two views while making the dimensions non-redundant. However, Barlow twins uses a single cross-correlation objective across both branches. VicReg makes the anti-collapse logic more explicit by splitting it into 3 terms. The variance term keeps every dimension alive. The invariance term pulls matching views together. The covariance term prevents different dimensions from carrying the same information. So VicReg gives us a clear recipe. Keep the views close keep the variance healthy, and decorrelate the dimensions. The trade-off is that VICREG still requires balancing multiple loss terms. That raises a natural question. Can we replace several anti-collapse ingredients with one principal regularizer? Instead of controlling only mean and covariance, we can regularize the whole embedding distribution toward a simple target: an isotropic Gaussian. An isotropic Gaussian is a balanced bell-shaped cloud, equally spread in every direction. Matching this target encourages the representation to use its space rather than collapse to a point. Checking directly whether a high-dimensional embedding is Gaussian is too expensive. The workaround is to look at many random one-dimensional projections. If enough random slices look like standard Gaussians, the full embedding distribution is pushed toward the right shape. This is sketched isotropic Gaussian regularization, or SIGREG. SIGREG is a clean anti-collapse rule. Keep the whole embedding distribution healthy, not just individual dimensions. Combining JEPA's predictive laws with SIGREG yields LeJEPA, in which one part predicts missing or future embeddings, and the other prevents the embedding space from degenerating. Now we can put the pieces together. JEPA tells the model what to predict: future or missing embeddings, not raw pixels. SIGREG tells the representation how not to collapse. Together, they give a principal way to train a world model from raw pixels, end to end, with only two loss terms. The first loss predicts the next embedding. The second loss regularizes the latent space so the embeddings stay well distributed. Applying LeJEPA to world modeling gives LeWorldModel. With around 15 million parameters, LeWorldModel can be trained on a single GPU in a few hours. That matters because world models are often treated as large, expensive systems. In the reported tasks, it plans up to 48 times faster than foundation model-based world models, while remaining competitive on 2D and 3D control benchmarks. Today, these results are still early, and many examples are still small scale, but the direction is promising. If you made it to the end, please drop a comment below, and I would love to hear your thoughts. Thanks for watching, and I'll see you next time.